is one where we can use all this, like all these equations and stuff that we've learned. So that's like, you know, the problem where you're just standing on the ground and you toss a ball. Well, we already know that the equations that we've used already work for that. So we already know that we're going to be good. But what if you were trying to figure out the path of this ball from a car that was already moving? It's like you have a car that's going along at, wow, this is going to be a terrible car. And it's moving at like 5 meters per second. You throw a ball out of it. In this case, because the car is moving at a constant velocity, you can actually just take this velocity out of your equation.
Okay.
So you remember when we did like relative velocities? So you'd have like a plane going this direction, another plane coming out of this direction.
Yeah.
And we found out what this plane's velocity would be relative to this one. So this would still be an inertial reference frame because you just have a constant velocity.
Okay.
So you can still figure out forces and acceleration. This is what it's getting into, is forces here. All the forces will still cancel out on a car that's moving at a constant velocity. And the physics will work. But what happens if you start trying to figure out these equations from a car that's speeding up? If you're trying to figure out the path of the ball compared to a car that's accelerating, say you just start at 0 and throw your ball out the window of the car, and then you speed up to try to catch the ball. Well, to the car, it's going to kind of look like this, right? You'll throw it out, and then as the car catches up, it'll slow down, and then as it speeds up, it'll actually look like it's falling back kind of behind the car, right?
Right.
So that's kind of where things get screwed up, is if what you're standing on isn't moving at a constant rate. So when you're trying to figure out forces, which is what you'll start doing pretty soon, you can add up, you can sum up all your forces, and the net force will cause an acceleration, as long as you're looking at something that isn't accelerating already. It's like if you tried to say that this was your fixed point, you had forces like this. Well, let's see. It's kind of like this. If you have a box that was sitting on top of a car, and say there's some friction holding it on, there'd be a force like that. And then there's the force of gravity pushing it down. And then there's the force of the car pushing back up. And then maybe there's like wind that's starting to blow it off. So this is all good. If the car is just sitting here, if it's just sitting still, then that would be an inertial reference frame. Because you can add up those forces, and whatever your acceleration ends up being after you do this, force equals mass times acceleration, that'll be the acceleration of the box. But if your car is, this even works if your car is moving along at, say, like a constant velocity of 5 meters per second or 10 meters per second, it doesn't matter. As long as it's a constant velocity, then it can still be an inertial reference frame.
So like as long as the car is like steady, that can be inertial.
Right.
Pretty much, right?
Yeah, then you can use it to kind of like compare against. But if it's not steady, then you can't use it to compare against anymore. So the reason he talks about this, so we know like centrifugal force. We've heard of that.
Mm-hmm.
So that's kind of like the reason inertial reference frames are important is because they get rid of these imaginary forces that we kind of come up with. So what happens with centrifugal force is you're going and you go around a corner, and what does it feel like happens to you?
So if you're going to the left, you like kind of, your body like kind of goes to the right.
Right, you feel like you're being thrown out this way.
Right.
And so we call that centrifugal force, right? We say, oh, when I went around the corner, there's a force that pushed me to go out, kind of pushed me into the door or whatever. But what would cause a force like that? Is there anything in your car that's actually pushing you that way?
No. So just the acceleration is, it doesn't like change. So when you move, your body kind of is trying to stay in that straight line.
Right. So what you're actually feeling is the car is accelerating that way, but your body tries to keep going this way.
Right.
And what actually happens is you keep going straight and you hit the side of the car, and then the car pushes you back in. So the reason you feel like you're being pushed into the wall is because you're not considering it in an inertial reference frame. Because you, compared to the car, yeah, you did accelerate to the right. But the car, compared to the ground, it actually accelerated, and you kept moving, kept going straight.
Okay.
So that prevents these like imaginary forces from taking place. The same thing happens when you're slowing down. If you stomp on your brakes, it feels like you're pushed into the steering wheel.
Yeah.
But there's actually no force that does that. So that would be looking at it in terms of something that wasn't an inertial reference frame, because your car, when you stomp on the brakes, is accelerating. It's negative acceleration, but it's accelerating. And so it's not a force that pushes you forward. It's just that you were already going that speed and your car decelerated, and so you ran into your steering wheel. So that's what it's kind of trying to help you avoid, is when you look at motion, to be able to say, is there a real force that's doing this? Or is it just an imaginary force because I don't have an inertial reference frame? And then the same could be said of like, if you're in an elevator, and the elevator starts accelerating to go up, what's actually happening, where's the actual force in this?
The force, like on the person or the force
Well, what's the force that the person feels?
is going down.
Yeah, he feels like he's getting pushed down into the
Right.
floor. That's what he feels. But what is the actual force in this?
It's going up.
Right, so what's actually happening is the elevator is being pulled up. So the elevator starts to accelerate. So this is the elevator's acceleration. Well, the person's acceleration is still 0 because he hasn't felt the force of the elevator yet. But once it starts moving up, his acceleration, he kind of feels like he's being pushed into the floor. But that's because his acceleration compared to the acceleration of the elevator makes it seem like there's a force there. So if you look at it in just inside the elevator and you ignore the fact that the elevator is accelerating, then you're not in an inertial reference frame. But if you step back and you look at the full thing, then you are in an inertial reference frame.